Oh, I don't see myself in front. Something's wrong. I don't see myself in front of the setup.
Yeah, that is very strange. Let me just
Huh.
see. Can you scooch over a little bit?
Well, I'm right in front of it. I mean, I'm right in front of the camera, just where I
That's very
usually sit.
strange.
I'm
Okay,
not.
well, hello everyone. Give us just a second to figure out our technical issues. We are using a new setup here. We installed a new operating system on our computer, and we are figuring out everything that is going on with it today. So give me just a moment to um, figure out what's going on here. I'm not sure why we have a weird delay here. All right, give us just a second, everyone. We are having a video issue. Our audio is working fine, but our video is causing us troubles. So, hello, everyone. Let me give you a quick welcome here while I work on these problems. So, welcome to the live stream, which is apparently not showing video. And so, while I troubleshoot these issues, Chris, why don't you go ahead and say hello to everyone? And why don't you give everyone a quick welcome? And I will kind of divert my attention for a second and see if I can figure out the video issues.
Okay, we're gonna let Matthew work on this. It's a strange one. I know a lot of you have been on these streams, and we've been doing them for years. It's amazing how many different glitches you can encounter. I mean, it's never completely smooth running forever. It just doesn't work that way for some reason. Anyway, we're good to be with you. I was gonna talk about a couple of issues, but I'm not going to get started until we have video because we need a stream that includes the video as well as the audio. So I'm just going to tread water here for a minute and hope we get things fixed as opposed to have to reschedule. Matthew, I'm hearing clicking from the camera, but I don't see it.
Yep, I think that's fine.
So when we get our video and this floor will be open for questions, I was going to talk about the moon missions. I was going to talk about Artemis briefly as an initial topic. Again, I will wait until we're fully rolling because we put these up on YouTube and it's not good to have something on YouTube that just doesn't have the video at all. There we go.
There we go. All right, I think we are back, everybody. We are fully rolling today. Thank you very much for your patience. My apologies. So we'll do, I'll quickly introduce myself. So I'm Matthew. I'm one of the course instructors for our online courses. So if those of you who are joining us not from our courses, we have some online classes and there's a link up in the chat. So if you scroll up, you can see a link to our Coursera courses. We have 3 of those. And if you found us through another way, then welcome today. Make sure that you click on the thumbs up icon, click on the like on our channel. Make sure you subscribe to our channel. Click that bell icon so that you can hear about upcoming live sessions. The way these live sessions work is that please post your questions in the chat. I will grab them from there. We do see all of the questions, so please ask your questions only once. I try to jump around a bit to give everybody a chance to have their topic or question addressed, and also to try and hit a variety of topics. So if we have a lot of black hole questions, I might jump around to get some other variety of questions, for example. So that being said, Chris, why don't you give us a quick introduction for your, you said moon topic, and then we will start grabbing questions from the chat.
Okay, the first topic I was going to mention was the Artemis 2 mission, which has been delayed by a month to a new launch window. So Artemis is NASA's going back to the moon after over half a century of humans not getting to the moon. Artemis 1 was unmanned and just demonstrated the spacecraft could get to the moon. Artemis 2 the one that's scheduled for any time now and has been delayed, was a crew of 4 that was going to go round the moon but not land, and Artemis 3 will be the landing on the moon. Artemis 2 was delayed within a day of launch. It had already got to the launch pad due to a hydrogen leak. So that's sort of the subsidiary topic here, which is that, Artemis is a big, complex, powerful rocket. But like many of NASA's rockets and many rockets in the history of the space program, it depends on highly finicky and volatile materials to get power. And the primary one, of course, is liquid hydrogen. So hydrogen is obviously explosively volatile. Light a match with the oxygen in the air and it just explodes. But it's also a very powerful producer of energy. And so it's a primary fuel with an oxidant for rocket fuel and has been for decades. But you have to work with it very carefully. It has to be kept at liquid temperatures, liquid hydrogen temperatures, minus 300 or more degrees Celsius. And the mechanical components in a rocket behave differently at very low temperatures. So the history of leaks, of hydrogen leaks and seals not working and ruptures in various places in hydrogen lines, and even occasionally in the hydrogen tank itself, is really a big issue in the space program. It was a hydrogen tank leaking and then igniting that caused the fatalities of one of the shuttle disasters. So it's clearly an issue that they have to take care of. So Artemis was delayed by a month, and we hope not more. But really, the history of delays of Artemis and the history of technical problems, a lot of it does come down to the use of liquid hydrogen as a fuel. And they're stuck with it, of course, so they just have to deal with this. But the engineering of these launches is clearly non-trivial. This will push the whole Artemis mission down the line as well. So Artemis is still the best prospect, the next prospect to get back to the moon, but it's on hold at least for a month until mid-March. And the second question I will address is, what is the future of going to the moon, including Artemis, but also other countries? So Artemis is the next game in town. Artemis 2 will, when it eventually launches, will go around the back of the moon and demonstrate the capability with a crew and test various systems for that kind of moon mission, a 10-day mission. Artemis 3 will be the landing on the moon. That will be the first human setting foot on the moon since 1972, since Apollo 17. And it's an ambitious mission. The scheduled date is still on NASA's website, says late 2027. I don't think anyone really believes that. I think it's almost certainly moving into 2028 and perhaps further. But by the end of the decade, it's very likely that Americans will return to the moon. And also these crewed missions include international astronauts too, so it's not all just Americans. Other countries that have ambitious moon plans are primarily China, and China is going back to the moon and has explicit plans for a crewed landing by the year 2030. So that's very similar to Artemis. They could win that race if Artemis is heavily delayed. India has plans to go to the moon. India's space program is moving very rapidly, and they have a crewed landing planned by 2040. Russia is not completely out of the picture. Russia is a not super wealthy space power anymore. The bills for their war in Ukraine are sort of bankrupting the country and not leaving much money for space research. But they have some historical capabilities with the Soyuz spacecraft and so on. And Russia does plan to go back to the moon too. They're a little cagey about their timeline and when the astronauts will land. And then there's another set of countries that have moon ambitions, not necessarily involving crewed landings. The wild card in all this is Elon Musk. So Elon Musk very recently has made pronouncements that almost speak to him making a pivot from his obsession with Mars to an obsession with the moon. Mars is famously his target for Starship, to send 1 million colonists to Mars eventually. That was always seen as grandiose and fantastic. And he's never met the timelines he's announced over the years, but that has been his major goal. He has, however, pivoted in public pronouncements to the focus on the moon because, of course, he recognizes that the moon is a week-long trip as opposed to a good fraction of a year trip to Mars. So the difficulty level is much lower, and it's perfect for his Starship. And his Starship vehicle was also part of Artemis's plan, so NASA depends on that spacecraft on that rocket working well. Why the moon? Well, Musk claims he wants to have a city on the moon within 10 years. So again, by maybe 2040. His timelines are always ambitious, and he wants to be able to launch satellites, rocket launch satellites, and hurl thousands or even tens or hundreds of thousands of satellites into deep space from the moon with its much lower gravity. And he also wants to create the first interplanetary internet and solar power stations in orbit. So he has the usual ambitious Musk-type plans, but he is giving his focus to the moon. So he will probably be the first private citizen or private company that will get humans onto the moon within, say, a decade. Okay, ready for questions?
Excellent. Thank you very much. All sorts of great moon news. It'll be exciting to see that part of human spaceflight take off. No pun intended. The first question for today is from Robert Brady, who's on with us live, who asks, could the Big Bang come from a super black hole? And I guess the more general question is, is there a relationship, or what is the relationship between the Big Bang, which is a singularity, or we think is a singularity, and a black hole, which we think of as a singularity?
This comes up occasionally, and I'll just give a simple answer. No, there's no direct relationship between the Big Bang singularity, the origin of the universe, and the formal definition of a black hole. Because we understand black holes to be gravitationally collapsed objects with an event horizon and a singularity at the center. But they're static objects. I mean, they will be rotating and have angular momentum, but it's not a dynamic situation. The Big Bang was a dynamic situation involving the entire universe. All space and time collapsed into one point. And so it is completely alien and different from the situation of a black hole. It's tempting to compare them, but I think astrophysically it's not appropriate.
Excellent. Thank you very much. The next question is from one of our live participants. Do we need a new branch of physics to combine quantum mechanics and the theory of relativity? And then kind of a related question is for developing the theory of everything.
Well, we definitely need new physics, a new branch of physics. That's sort of semantic, so I'm not sure what the distinction would be, but we absolutely need new physics to unite general relativity and quantum theory, because each of those theories is self-contained and has enormous explanatory power. Those are the two most successful physical theories of the modern era. But they don't work together well. The terminology, the phenomenology, the formalism, and the physical basis is completely different. So yes, it will almost certainly need a new type of physics to combine them. String theory has held promise and has been the one that everyone looks to, but string theory progress has been relatively slow in the last 10 or 20 years. And it's not making firm enough predictions for people to be confident that we can apply it to the early universe, for example, and make therefore a theory of everything. This is probably the most challenging problem in physical science, to come up with a unification theory. And there's 100 or so very clever theorists working on this hard with different approaches, but I would say progress has not been measurable in the last few years. So it remains an extremely difficult and possibly intractable problem.
The next question is from Boomy Deep Dive Sai, who asks, what causes magnetars? I mean, how can a star attract itself towards the center to become the size of a city and explode?
A magnetar is a magnetized, highly collapsed star, has the highest magnetic fields known in astrophysics in the universe. I think the fields can go up to 10 to the 16 or 10 to the 17 Gauss, which is a crazy number. That's 1,000 trillion times stronger than a refrigerator magnet. A star like that can easily form, or can readily form, because it's a very massive star, so it will gravitationally collapse at the end of its life when there's no fusion support. And because magnetic fields are entrained in a plasma, the magnetic field that it had as a normal-sized star will be squeezed and compressed to enormous strength in the collapse. So we have a ready explanation in the collapse of a massive star at the end of its life of how you can generate a phenomenally strong magnetic field. Not all stars have the same strength magnetic field, so these are indeed a particular class of stars that start with high magnetic fields and are amplified by the collapse and compression. And they're rare objects. They are much rarer, for example, than pulsars, probably 100 times rarer than pulsars.
The next question is from Almar, who's on with us live, who asks, what makes interstellar objects like 2I Borisov, which is like an interstellar comet like Oumuamua, what makes objects like that or like those different from typical solar system comets?
Well, if we have a true interstellar interloper, and we seem to have had three of them in the last couple of years, and there may be more, and there obviously will be more because we're just getting better at spotting them, that's not completely unreasonable. Solar systems are separated by wide gulfs of interstellar space. So the distance from us to, say, the nearest star, Proxima Centauri, which may indeed have its own comet cloud, is large. It's hundreds of trillions of miles. But comets, of course, are mostly captive. They're mostly gravitationally retained in the solar system in the equivalent of an Oort cloud if it's another star. But occasionally they will get ejected because their instabilities or passage of nearby stars will disrupt the Oort cloud, sending some comets into the center of the system and ejecting others. And those ejected comets, some small fraction of the total, and the Oort cloud we think contains for the solar system about 1 trillion comets. So it's a big reservoir. So even a tiny fraction of 1 trillion being ejected is a lot being sent into interstellar space. With space being so large, the odds of one of those ejected comets intercepting another star system is low. So right away, we know that interstellar comets coming to our system are going to be rare. The fact that we've seen a couple in recent years, I think just means we're better at detecting them. But it may be a sign that more comets are ejected from other star systems than we anticipated. They're exciting, of course, because they give us an insight into another distant star system by the direct transmission of material to our solar system, which we can then study spectroscopically, and maybe eventually we could even land rockets on and capture that material and understand it better. So they are very important objects.
The next question is from an email. One of our participants sent an email. Wendy Traver asks, Brian Greene stated that he believes that the ultimate outcome of our Mars missions will be to establish an outpost with rotating crews akin to Antarctica, a sustained presence rather than a colony with thousands of people. And that will truly be a great accomplishment for humans. What are your thoughts?
Yeah, I agree. The idea of a colony is very much in the future. I would even say 100 years in the future. So the first goal is just to have a crew land on Mars successfully and spend some time there. And there'll be a minimal crew, maybe 4 people. 2 would be too few, 6 maybe too many energy requirements. So 4 is probably the sweet spot. And then you can extend that. Each crew, if you continually resupply or have crews going out every year or so, you can gradually build up infrastructure, habitats for a colony, but it will still be a minimal base. You're basically building a Mars base for a modest number of inhabitants. And that is a plausible development model. I think going directly to a colony of hundreds or thousands of people is implausible. There's too much infrastructure. You need too much equipment, too much material. The energy costs are high. Getting to Mars requires a lot of food and a lot of oxygen, so you got to bring it and you got to carry it, and the cost of rocket fuel for that is high. So I agree with Brian Greene that we're likely to looking at a small crewed presence with rotating crews every year or so.
Excellent. The next question is from one of our live participants. Troy Thomas asks, is there proof of expansion within our galaxy or within our solar system, or can we only observe it on much larger scales?
So the expanding universe applies on the largest scale. So the expanding universe is caused by the space-time continuum, space-time itself expanding at a rate that's been varying since the Big Bang 13.8 billion years ago. So this is the fabric of space-time itself. And so galaxies receding from us or moving away from each other are being carried apart by the expansion of space-time. However, within a galaxy, the contents of the galaxy are held together in one place, in one system that doesn't really change over time by gravity, by the gravity of the visible stuff we see, and by 5 or 6 times more dark matter that's mostly in a large extended halo. So within a galaxy, We don't see expansion because the galaxy is kept as a self-contained object within the expanding universe by its own internal gravity. And the same is true on the scale of solar system or any smaller scale within the galaxy.
The next question is from one of our live participants who has a rocket-related question. Why does NASA use hydrogen as a fuel rather than methane?
Um, there are historical reasons for this. Hydrogen is essentially, you get the most energy release per gram of fuel from hydrogen. Methane is also good, and there are classical rocket fuels, liquid fuels like methane is one example, hydrazine is another. So these are just highly volatile hydrocarbons. But hydrogen has the most energy release per gram, and that's the simple answer why. Is it worth dealing with the complications and difficulties of hydrogen for that benefit? Well, maybe if you need an extremely powerful rocket, if you're going to go to Mars or you're going to launch people to the moon, you do sort of want the most efficient fuel possible. And the commitment was made by NASA decades ago, of course, and they built up a lot of expertise in working with hydrogen as a fuel. So they don't, in this end, want to jettison that.
The next question is from Walla Samsung, who asks, what exactly is inside the hydrogen atoms in space?
So hydrogen atoms in space, especially in interstellar and intergalactic space, they're not typically neutral atoms. That's important to realize that the intergalactic and interstellar medium, especially the intergalactic medium, despite the coldness of space, most of space has the temperature of the microwave background, 3 degrees Kelvin. The radiation temperature of space is quite high because space is filled with X-ray emission, and that X-ray emission comes from energetic stars, from supernova remnants, from the ultraviolet radiation that massive stars produce. And that radiation is powerful enough to ionize hydrogen. So we've known for a long time that the hydrogen we see in intergalactic space is almost completely ionized, which is to say the electrons have been stripped off it because of its high temperature, because the temperature is millions of degrees rather than a few thousand, and you only need about 3,000 to make hydrogen ionized. The neutral fraction of the gas, so the fraction that's actually hydrogen atoms as opposed to ions, is about 10 to the minus 5, so 1 part in 100,000. So really most of this gas is completely ionized, so the protons and electrons are not attached to each other.
The next question is from Mary, who asks, is the black hole in the center of our galaxy dangerous in any way for our solar system?
No, the black hole in the center of a galaxy is no danger at all. That's good to know. It's a 4 million solar mass black hole, and the work to understand that was done in the 80s and 90s, led to a Nobel Prize to Andrea Ghez at UCLA and Reinhard Genzel at Max Planck Institute in Germany. And they put a mass on it. They measured the mass. And 4 million solar masses sounds big, but in the context of the center of our galaxy, there's many times that number of a mass of stars in the central star cluster and central regions. So the black hole does not even dominate the mass inventory of the center part of our galaxy. And from our distance, 28 or 27,000 light years away, that black hole, we just do not feel its gravitational pull. It's too far away and it's too small relative to the other components of the galaxy. And so therefore there's no chance of the solar system being disrupted or pulled into the center of our galaxy. We will continue in our circular orbit of the disk of the galaxy for the foreseeable future.
Our next question is from Dave Wells, who's on with us live, who asks, with the recent revelation of new data from the Cassini mission, which moon do you think has the most probability of finding life, Enceladus or Europa?
Okay, so it's tricky, and nobody knows actually. Enceladus has all the ingredients for life. We know it has subsurface water, which is leading to the ejection of these icy geysers. We've had the Cassini mission sniff those jets and find salty material and salts. So there's dissolved salts in that liquid ocean. They don't indicate life or not one way or the other, but there's certainly a prospect for life. Cassini, of course, was a mission out to Saturn, and so Europa was not what Cassini looked at. Europa has a good plausibility for life, but the other target that Cassini was a part of investigating was Titan, the biggest moon of Saturn, which the Huygens probe landed on. And Huygens has hydrocarbon lakes. They're very cold. And really, no biologist is willing to bet that there's life in that strange chemical mix of ethane, methane, a little water, and a little ammonia, all at very low temperature. So if you look at it that way, then perhaps Enceladus is the best bet to find life in that outer part of the solar system.
The next question is from one of our live participants who would like to know if someone is starting their starting their journey in the field of astronomy and astrophysics, where should they start?
Well, it depends what your goal is. I mean, if your goal is just to be a lifelong learner and learn as much as you can about the subject, then you can take our one of our MOOCs, our Massive Open Online Classes through Coursera or Udemy. You can read books, you can watch amazingly good and enormous number of YouTube videos. You want to find a good, reliable interlocutor or station for YouTube. Not all YouTube videos are equally accurate on astronomy. So you can learn a lot from a MOOC, from YouTube videos, from reading books. I mean, if you want to take a formal course and be trained in astronomy, then you have to enroll at least as an auditor in a university class, if not matriculate as a student. But that would be a higher level of commitment, because at that point you're taking astronomy courses for a grade, and it would presumably have to fit the purpose of a degree that you were taking. So that's a quite different decision to make.
The next question is from one of our live participants. Could you please clarify how items or objects can travel faster than light?
Individual objects cannot travel faster than light. Light is the maximum speed. So if we try to accelerate something, a physical object, from a macroscopic object like a spacecraft down to a microscopic object, subatomic particle, we can't make it go faster than light. Big objects, human size, we can't make go faster than light. We not only can't do that, we can't send them even to 1% of the speed of light. Subatomic particles in accelerators are traveling at their collision energies at 99.999% of the speed of light. So we can definitely approach the speed of light for a subatomic particle. But no physical object in the lab or in the world that we have technology to control can be made to go faster than light. That's a premise of special relativity, Einstein's theory, and it's held up in observation for 100 years.
The next question is from Keith, who asks, or Keith Trish Crum, who asks, is there an issue? I guess they've heard about something. Is there an issue with the Orion heat shield, or have you heard about any issues with the Orion heat shield?
There are always concerns about the heat shields of spacecraft, because the reentry, especially for Orion, this is a good point. Heat shields are an important part. All spacecraft do a very high speed reentry, and essentially they're using drag, which creates at the collision interface of the atmosphere and the spacecraft, creates a lot of heat. They're using that drag to slow down to the point where they can use a parachute eventually. So spacecraft, all going back to Mercury, Gemini, Apollo, etc., had heat shields, and those heat shields mostly work, but they have to be super strong to deal with those forces. Now, Orion is special in the sense that it's going to be the fastest of these rockets. It's reaching speeds of, I think, 25,000 miles an hour. So it's about the fastest spacecraft we've had in play for a long time. And so when it re-enters, it's coming in at a phenomenal speed. And so it's created concerns about the Orion heat shield, which of course has been extensively tested and so on. I think there's an abundance of caution in the Artemis project over the intense speed and therefore heat generation of the reentry, and the fact that they've never really done this level of heat protection before within NASA. So they don't know how well it's going to work. Artemis 1, however, was successful, so it dealt with also the reentry issue. So there is at least one success to indicate the heat shield works as advertised.
The next question is from one of our live participants. If the speed of light were different in one direction than the other, how would that change our understanding of the age of the universe or distant stars?
It's an interesting hypothetical. If we think the laws of physics are uniform and isotropic, that is, they are the same at every location in space and at all distances back in time. But we haven't verified that entirely. So if hypothetically the speed of light was different in different directions in space, first of all, there's no physical mechanism by which we think that could happen. So this is very hypothetical. Then yes, it would create a situation where look back time, light travel time, and look back time were different depending on where you looked. And so you would see different regions of the old universe, different volumes of the old universe looking in different directions from the Earth. It would be quite a strange situation.
In kind of a related question, is the constancy of light a law or nature, or is it just a human-made definition to make our math easier?
No, it's a constant of nature. So the constancy of the speed of light is not an article of faith because we've measured it to have the speed it has, and no one's ever seen a variation of that. But it's built in with the bricks to special relativity. In other words, the theory of special relativity is predicated on the constancy of the speed of light, the fact that it's an absolute number in the universe, 300,000 kilometers per second, doesn't depend on the observer situation or the relative motion of observers, and all the consequences of special relativity, which is Lorentz contraction, the shrinking of things in the direction of motion, the dilation of time, the stretching of time as speed increases, and the growth of mass of an object approaching the speed of light. All of those things flow from the initial premise, which has been validated experimentally.
The next question is from one of our live participants. What do you think are the odds of the leopard spots that were found on Mars by the Perseverance rover? What are the odds of them being of biological origin? Have there been other signs with higher odds, in your opinion?
There's not enough good data of the right kind to say much about the biological nature of the leopard spots. So there's been a series of interesting organic compounds and formations that Perseverance rover has found, and it has a mass spectrometer, so it's able to vaporize material from rocks and determine the mass spectrum of the ingredients in it, and therefore know the chemical composition. And so there are definitely, as in the leopard spots, but not just the leopard spots, there are places where there's a high incidence of organic material, where you see many of the ingredients for life. But these are not exact biological relics. You're not looking at fossils or microfossils by any means. And the Perseverance rover is not able to do an assay of biological significance, in other words, to parse the DNA. So at some point, all we're going to get is provocative indications that these are potentially habitable signs of Mars. And that's probably what we've been getting for the last few years from the rovers.
The next question is from discussion about printing being on the moon or Mars. How feasible is it that the technology can be employed in those environments?
You were starting to chop up, but I think I got the question. So 3D printing is a powerful technology for space, and it's increasingly used. So 3D printing has been used on the International Space Station. There are 3D printers on the space station that help with experiments and help generate components that break or new components. 3D printing more generally will be a very powerful way of developing our capabilities in space. 3D printing on the moon, for example, using the lunar regolith or soil as the raw material, we'll be able to create construction material. You can also use 3D printing to generate tools themselves from metals or from carbon. So 3D printing is extremely important in terms of how space develops and how our technologies in space develop. And the key here is that it's expensive and energetically disadvantageous to bring a lot of material up from the Earth against the Earth's gravity. And a lot of stuff, construction material is heavy. So it's far better to make it with local materials. And 3D printing is sort of the key to be able to do that.
The next question is from Llama Shadow Witch, who's on with us live, and asks, how bad is the space junk problem around low Earth orbit? And is there any way to clear out or reduce the amount that is actually feasible at present?
The space junk problem is bad and getting worse. It's a matter of great concern to astronomers and to space community on a larger scale, because if it gets too bad, then it could threaten the entire activity, which is starting to be a significant part of the economy. The space business itself is now valued at several $100 billion a year worldwide. So that's a pretty big chunk of change. And if you couldn't operate in near Earth orbit, then you have to give all that up. So the number of NEO satellites is about 20,000, going up rapidly with launch of different constellations of satellites. Elon Musk talked cavalierly about 1 million satellites that he wants to launch. Well, even setting that aside, much more low Earth orbit satellites means more collisions, means more space debris. The debris never goes anywhere. It doesn't deorbit. Some of it does. If it's very low altitude, it will have some drag in the upper atmosphere and therefore deorbit and burn up. But most of it will not. And it will continue to degrade by collisions into smaller and smaller pieces, all of which are damaging. So it's a huge problem. I mean, it's got the attention of everyone in the space community, but remedies are hard to find, given the ambitions of space entrepreneurs to put enormous numbers of new satellites up there. It's hard to see how it can get better, because the cleanup or mitigation strategies are not really very efficient or effective. It's just too big a volume or a space to sweep material up, or use magnets or harpoons or lassos or all the clever technologies people have thought. These will not solve the problem as we currently understand it.
The next question is from We See the Same Moon, who's on with us live, and asks, how can the relationship between time and space best be understood from the cosmic perspective? And what role does gravity play in this regard?
The best way to understand the relationship between time and space is that the universe is like a time machine. As you look out in space, you look back in time because of the finite speed of light travel. And so that's an amazing feature of the universe, that we don't see the universe with our telescopes as it is now everywhere. We see more distant regions as they were in the past due to light travel time. So you could think of that as a limitation if you like. You want to know what those distant regions are doing now. But in a way, the universe being a time machine due to finite light speed is a benefit, because it lets us do cosmic archaeology. We can look back in time towards the Big Bang due to the finite light speed travel. Now, if light speed were infinite, that whole situation would be totally different. And that would actually be a very counterintuitive universe where we see everything all at once.
The next question is from Dwayne Harris, who's on with us live, and asks, is the asteroid belt a failed planet or one that was destroyed in some way?
That's a good question. The best guess is that it's a failed planet, not a planet that was destroyed. But the evidence for that is not totally convincing. To put a number on it, if you swept up all the asteroids in the asteroid belt, they're really not, it's not much mass. It's about 4 or 5% of the Earth's mass. So even if you swept up the debris that's there now, it wouldn't form a significant sized planet, certainly not a giant planet that you would expect at that distance from the sun. It's considered more likely that it's a failed planet because if it were a large planet that was destroyed, there probably would have been other disruptions to the orbits of the other planets. For it to just be a failed planet means the debris that's left after some is scattered out of the asteroid belt, and that's why you end up with only 5% of the Earth mass. There was probably a lot more originally. It would have no real impact on the other planets and their orbits. It's that just the asteroid belt is self-contained in that way gravitationally.
The next question is from AKA Great, who's on with us live. Hello, Professor. Since the laws of nature say that energy is conserved, Is there a definite number or amount of energy that the universe began with? And if so, do we know the value?
Yes, I mean, in a sense, with the Big Bang model, we can put a number on different types of energy in the universe. We can put a number on the mass energy of the universe in the form of matter and radiation, because we can weigh the universe, we can measure the amount of normal and dark matter, and we know the number of photons with about 1 billion photons for every particle in the universe. We can do that inventory. And so, yes, we know what that number is pretty accurately.
The next question is from Christos, who's on with us live, who asks, Good evening, Professor. Can Proxima Centauri B hold on to a significant atmosphere on its dark side and terminator zone?
I don't think we know enough about Proxima Centauri b. First of all, Proxima Centauri is the nearest star system. Proxima Centauri b is a component of the multiple star system where we think there's an Earth-sized or roughly terrestrial-sized planet. And so it's a subject of great observational scrutiny from the exoplanet community. But we don't have a measurement of its rotation speed. We don't have any direct diagnostics of biomarkers in the atmosphere. So I don't think we can talk in detail at all about the way the atmosphere of Proxima Centauri b behaves with current data.
The next question is from Dragon67, who has a question about telescopes. So I assume they mean personal telescopes, but I think we could expand this. What is the most effective telescope to use when viewing planets? Can you talk about how astronomers view planets and which telescopes are best for that? And then how would a beginner look at planets?
I mean, if you want to look at the planets, the good news is you don't need a big telescope at all. You don't actually want a telescope with too wide a field of view, because you're looking at small objects and you want the highest resolution across that object. So you want as good a magnification as you can get, 30 or 50 times at least. And a small amateur telescope should be able to do that and will give you pretty good views of the planets. Not only that, you'll be able to see the moon systems. Certainly, you won't be able to see Phobos and Deimos unless you have a very impressive amateur telescope. You'll certainly be able to see the Jovian moons, the Galilean moons, those 4 and sometimes 5 or 6. Number 5 and 6 in the relative sizes. You'll be able to see the largest moons of Saturn, like Titan. So I think small telescopes are all you need. Professional astronomers do observe planets, of course, and they use somewhat larger telescopes, but they don't really need to go much larger than a meter to observe the planets. And telescopes like Hubble and James Webb, which is a huge telescope, have observed planets for particular purposes. But those are pretty easy targets for the kind of equipment you can buy for a couple $100.
The next question is from Wendy, who sent an email. Isn't the Big Crunch, or is the Big Crunch theory of the end of the universe at odds with entropy?
Yes, this goes back to Stephen Hawking in the 1970s. He was looking at the possibility of an oscillating universe or recollapsing universe, because it was out there in the ideas of cosmology in the mid part of the 20th century. And he calculated that if you went through a singularity and somehow had a bounce, entropy would increase through the singularity. He did that calculation. No one's refuted it or found it to be wrong. And therefore, that sort of applies a symmetry, an asymmetry. There's an arrow of time associated with that, where entropy continues to increase. And if you have an endless oscillating universe, why is the entropy not infinite? Why is it a particular time in the history of this oscillation that we measure entropy, which is actually quite low, given how high the entropy of the universe could be? So that was one of the strong reasons from physics, from astrophysics, why the oscillating universe fell out of favor. The second, maybe more important reason, because it's observational, was that the universe simply doesn't have enough matter, dark or visible, to recollapse.
Excellent, thank you. The next question is from Noman5, who asks, I became a Plutophile after reading the book Chasing Horizon, and have read a half dozen books on Pluto since. Do you know of any online courses specifically about Pluto, or do you have any recommendations for other resources to learn about Pluto?
No, I don't know of any books written particularly about Pluto. Michael Brown has written about dwarf planets, including Pluto, in a book with the famous title, How I Killed Pluto and Why I Had It Coming, from 10 years or so ago. It's a good book. So there are books, for example, that talk about outer solar system objects, Kuiper Belt, and dwarf planets, including Pluto, but I don't know of one specifically about Pluto, nor do I know of any courses that are specifically on Pluto. If you want to read more about Pluto, however, there have been many scientific results published from the New Horizons probe as it sped past Pluto and saw incredible geological features on Pluto. So you can do sort of Google Scholar search on New Horizons or Pluto, and you'll find some very interesting papers. Some are quite technical, but there are review articles not so technical, and that will give you that incredible insight we got into Pluto from that flyby some years ago.
The next question is from Arif Roni, who asks, how is the Artemis mission different from the Apollo moon landing in the context of Moore's law and the advancement of technology, where Apollo had a kilobyte of memory? How have the advances in computing affected it?
Right. So the core technology, the rocket technology, has advanced somewhat since Apollo. The Space Launch System, SLS, is the most powerful rocket NASA's ever built. So it does finally eclipse the famous Saturn V rocket, which was a great rocket that never failed, either in tests or in the Apollo missions themselves. So the rocket technology has advanced, but probably only incrementally. But yes, the information technology has advanced dramatically. The computers that Apollo used were extremely primitive. Any phone, any smartphone that anyone has, even a basic model, would have had much more computational power than the onboard computers for Apollo. Artemis obviously has high-end computers, miniaturization. It has high bandwidth communication with the Earth. That's another thing that's different. The bandwidth of information transfer between an Earth and a moon orbit is much higher than in Apollo. There was a stranglehold on the bit rate for that. So I would say that's transformational. It's just going to help make the mission go more smoothly. It's going to help gather more data and send it back instantly to the Earth. And it's going to give people a richer experience, the ones who are watching it on television.
The next question is from Burns Hennessy, who asks, is there any truth in the concept that the universe is expanding faster than the speed of light?
It is true in some aspects. So the universe is expanding, and it's expanding at an accelerating rate due to dark energy. And there was a time in the distant past, not too long after the Big Bang, when every region of space was moving away from every other region of space faster than light. So the universe did have superluminal expansion, faster than light speed expansion early on. And that means, in turn, that there are regions of space and time that we can't see and may never see, actually, especially given the universe is now accelerating. So there was a time when dark matter was slowing the expansion rate down, and there was a prospect that we might see those more distant regions. But now the odds are that we won't. So yes, there's superluminal expansion of the universe, which doesn't violate special relativity, because special relativity does not apply to the whole universe. You have to jump to Einstein's superior theory of gravity, general relativity, to explain that. And there's no speed limit attached to the expansion of the universe, like there is in local physics with the speed of light.
The next question is from Dragon67, who asks, what technology is used to analyze planet components, like, iron, hydrogen, like what planets are made of?
In the solar system, of course, it's remote sensing, because we've only been to Mars. We've only sort of done geological work directly on one planet. So if we're talking about elsewhere in the solar system, we have to use spectroscopy. So reflectance spectroscopy, you shine light off a rocky planetary surface, and the spectroscopy tells you what the minerals are, what the general geological composition is, and that's our most detailed information about terrestrial planets. For gas giants, of course, we don't get that information. We think there are rocky cores for all the giant planets, Saturn, Jupiter, Uranus, and Neptune, but we can't see them directly. So we don't really know what those cores are made of. And for exoplanets, that information is still in the future because we don't have reflectance spectroscopy of the incredibly faint light from an exoplanet, so we can't do the same work on an exoplanet that we could do on a planet in the solar system.
Excellent. The next question, I think may have to be our last one. We have to go a little bit early today due to another commitment. So I think we'll take this one as our last one, just so we have plenty of time. Jimco asks, if we could observe the universe for 1 million years, what unexpected phenomena might we discover?
That's an interesting question, hypothetical. If we observe the universe for 1 million years, us or our descendants, or we had a long span of data, modern astronomy is only a few hundred years old, we wouldn't see much difference in the cosmic scale of the universe. The expansion rate would increase due to dark energy, and we probably, over 1 million years, we'd probably actually get to measure directly the expansion rate changing. So that would be interesting. The other things we'd observe over 1 million years, if we had that kind of data, of course, was enormous number of transient events. So we would be able to observe enormous numbers of supernovae or dying stars with observations over 1 million years, because those supernovae are rare events. There's only one per galaxy per century, the Milky Way being an example. There hasn't been one for 400 years. But if you have 1 million years of data, you're going to have seen hundreds of supernovae, not only in the Milky Way, but in other galaxies too, if they're bright enough. That's a phenomenal amount of data. So for some transient phenomena, and supernovae are the best example, but there are others, 1 million years would give you a sort of treasure trove of data. So it's a very ambitious goal for astronomers to plan an observing program that lasts not just a few years or 5 years as I've done in the past, but one that lasts 1 million years and gets you much further down the road to understanding. That was a good question to end with, and we had the usual good coverage of subject matter. Sorry for our slow start. I don't remember if we have one on the schedule, but we'll be back with you in a couple of weeks.
Excellent. Yes, we do have one scheduled. The next one will be in 2 weeks on Wednesday, February 25th. So we will see you all then. And that's a good time to remind you, give the video a thumbs up so that it gets out to other YouTube viewers. Make sure you subscribe to our YouTube channel and click the bell icon so that you find out about upcoming sessions. And if you want to, scroll all the way to the top and join our listserv so that you hear about announcements for upcoming live sessions. I want to thank you all so much for joining us today. We will see you in 2 weeks. Take care, everyone.